Hi everyone, and welcome to the third part of the mini course. So in this talk, we're going to discuss Theorem A and the connections between rigidity and rigidity problems and the instability material, which we discussed in the last talk. So firstly, I have to set up some standard background material concerning the moduli space of Einstein structures. Throughout the talk, we're going to be exclusively dealing with an Einstein manifold, and we'll scale it to have a unit volume. So if we consider GE as an element of the space of all metrics with unit volume, we have an infinitesimal description of the space by studying the slice of the action of the diffeomorphism group on M1. So this gives us a chart for the moduli space, and the subset of Einstein metrics inside this slice is called the pre-moduli space of Einstein metrics, which is going to be denoted by epsilon of GE, uppercase epsilon. So the starting point of the theory is an infinitesimal description of the moduli of the pre-moduli space. This is all due to the work of Koiso, and he studied what are called Einstein infinitesimal deformations, EIDs. So by definition, this is going to be a element of a symmetric two-tensor whose trace is 0 and divergence vanishes. These are called TT tensors as well, and which satisfy the condition that the Laplacian of H plus twice there's a natural action of the curvature tensor on symmetric two tensors, and so this equation is satisfied. So right now we're going to denote the space of these of such objects by epsilon, lowercase epsilon of G. To see the connection with stability, you see a starting point is that the operator we were concerned with studying last time is really sort of the same things. So we had the Lichnervitz Laplacian plus twice the Einstein constant, and if you a direct computation shows you that that's the same thing as this operator here. So being neutrally linearly stable is where you have a symmetric tensor which satisfies that this equation is equal to 0 is exactly the same thing here. Okay, so obviously there's sort of an immediate connection between the two topics because you're studying the same equation. Okay, so somehow this is our picture within the moduli space of M1. We have our Einstein metric GE, and the question we're interested in is rigidity. So is it the case that this metric is isolated in this moduli space, or does there exist a curve? If it's not, there must be a curve of Einstein metrics passing through that point, and somehow EIDs describe the tangent space to this curve. So let's sort of study this a bit further. The main theorem which makes this more rigorous is due to Koiso, who proved that within the slice there is a real analytic submanifold Z or Z, such that, well, the tangent space of Z is the space of EIDs, and Z contains the pre-moduli space as a real analytic subset. What does this mean? So if Z is zero-dimensional, then we have an isolated Einstein metric. And isolated metrics are equivalently called rigid metrics. So Koiso then used this to show many examples of rigid Einstein metrics. So for example, most symmetric spaces. So he explicitly computes this for like large for symmetric spaces. And if this epsilon, if this space of is 0, right, what this means is that the tangent space of Z vanishes, and so but the tangent space contains the pre-moduli space, so therefore the pre-moduli space is empty, and so there's no deformations. So the sort of interesting question is the following, which naturally somehow comes up because you want to understand, this is an infinitesimal description, and really you want to understand, okay, does this infinitesimal object actually arise as a genuine tangent to a curve of metrics in our pre-moduli space? So in other words, can you find elements, non-zero elements in epsilon of GE, which actually arise as the tangent to curves of metrics? And there's a famous example of Koizo. So he showed that CPn cross CP1, he showed that this Einstein metric is isolated or rigid. So it's isolated in the moduli space. There does not exist a curve of Einstein metrics passing through it. But at the same time, this infinitesimal description, epsilon of G, is non-zero. So this does admit infinitesimal deformations, but none of them integrate up to actually correspond to a genuine curve passing through the manifold. That's the point. So that's somehow an answer to this question. Well, I mean, that is an answer to this question. And it's very well known, right? So this is a standard example that everybody gives. Okay. So we want to explain a bit more his approach and how Koizo developed this machinery, because that's what we want to do to compute it. What we want to do is we want to prove that SUN, where n is an odd integer, so that's with the bi-invariant metric, that's a symmetric space. It's a very fundamentally, one of the first examples of an Einstein manifold. And we want to prove that when n is odd, this is going to be rigid or isolated in the moduli space. And we're going to use this machinery to do so. So just delving a little deeper, how Koizo's approach works is he develops an obstruction to integrability. And this arises by considering a functional E on the moduli space of metrics. So given a metric G, you output the Ricci tensor of G minus the integral of the scalar curvature divided by the dimension times G. It's a nice exercise in definitions and taking traces to show that E of G is equal to 0 corresponds to the Einstein metrics. So if we have a curve of Einstein metrics going through our initial Einstein metric, corresponding to whose initial derivative is given by this element, a distinguished element H in our space epsilon of G. Well, if we're actually moving along a curve of Einstein metrics, then this function will always be 0, and so the derivative in this direction will be 0. All right. So somehow, because we know this space is real analytic, Koizo was motivated to sort of define an element to be integrable to order k if you can find symmetric tensors h2 up to hk, so that this curve will satisfy, so that all derivatives up to order k will vanish along the curve. So this is a generalization of being integrable to order 1, right? It's formally integrable then if you can actually effectively construct a power series. So we start at 2 because the h1 is obviously just going to correspond to h. That's the initial direction you go in. And if you can have what Koizo's structure theorem tells you is if you're formally integrable, then you must actually genuinely come from a smooth curve of Einstein metrics. Right? This just effectively comes from Koizo's structure theorem because you know that the space Z is real analytic. So you know it's real analytic and you're constructing power series, it's clear. So in particular, if you want to show that your Einstein metric is rigid, well, if it's not, I mean, I guess you consider the contrapositive or something. If it's not rigid, then if you genuinely have a curve of Einstein metrics, then you can look at the derivatives of our functional, and they must all vanish. So if they don't vanish to some order, then you cannot be passing through a curve of Einstein metrics. That's the logic. So motivated by this, he considered the first natural thing to do, which is to look at the second derivative. Okay, so it's being integrable to order 2. So if you compute this out, sort of taking derivatives in the appropriate spaces, the second derivative of E, as you pass along this curve G of t, where the initial derivative is h, you get 2 derivatives E dash dash of hh, plus then there's a derivative of E in this direction. But if you're at an Einstein manifold, if you're moving through a curve of Einstein metrics, this will vanish. And so you get this quantity. And Koizo proved that h is integrable to order 2 is exactly the same as this element, E prime prime of hh, being perpendicular to the space epsilon of G. So what this means is that if it's going to be integrable, so if it's going to be integrable to order, if it's going to be integrable, it's going to be integrable to order 2, which means that this operator, this element cannot lie in the same space as epsilon of GE, and an element of epsilon of GE is H itself. So therefore, if you were to take the L2 inner product of these guys, you will get 0. So what's natural to do, this is Koizo's obstruction to integrability, is to say if this quantity does not vanish, then you can't be integrable. So this is effectively, you project E prime prime onto the space of infinitesimal deformations. That has to be 0 to be integrable of order 2. So in particular, when you take the inner product with H itself, you must get 0. That's what I'm saying. Okay, so then Koizo actually computes this out in local coordinates where everything is taken, where the inner products are taken with respect to the appropriate bundles. And this is the tensor expression you get. And this is how he shows that spaces are this is an obstruction to integrability. So in particular, if you can show this quantity is not 0, then there cannot be a curve of Einstein metrics passing through G with initial derivative given by H. That's sort of the upshot. So maybe firstly, I'll start by proving Theorem B from the, or discussing Theorem B from the introduction, which was this connection, right, between instability under Ricci flow and integrability. Okay, so I guess we've already defined nu before, and now I've defined Koizo's obstruction. And if you look at an essential Einstein deformation for an Einstein manifold, so here we have an Einstein manifold where, for various reasons, I'm going to state 1 over 2 tau as being the Einstein constant, changing notation slightly from the previous talk. And this is your family, this is your perturbation, you perturb in this direction. Then the third derivative of the new functional is related to the Koizo's obstruction by this quantity. Now, I guess connections between integrability and stability were already floating around for sure in the literature. For example, Shisam had this work where she was studying integrability, and under an integrability assumption, she could prove neutral linear stability implies dynamical stability. And so it was known that these topics are connected. How do we prove this theorem? Well, we effectively just compute everything out. I guess it's an interesting sort of philosophical question as to why it's sort of true. Somehow they both the new functional and Koizo's functional arise from considering taking derivatives of functionals involving scalar curvature. And, you know, both of them, so this is of course restricting the new functional to the space of EIDs. So you see the perturbation H is the same in both. So therefore they solve the same equation. But yeah, this gives us a very nice connection between studying instability of Ricci flow and studying integrability of Einstein metrics. That's maybe the key point. Of course, if you want to show an Einstein metric is isolated, it's not enough. You have to show that no matter which direction you go in, so no matter which element H you choose in epsilon of G, you have to show that this quantity doesn't vanish in all directions. Okay, because if it doesn't vanish in this direction, if it vanishes in one direction, well, it might not vanish in another direction. And you have to do it for all directions, because you right, so that you know no matter what direction you go in, there is no Einstein metric for which no curve of Einstein metrics such that that's the derivative. In other words, you have to prove that I of H is non-zero for all perturbations H. But somehow you can see here it's going to be much easier to prove instability, because if you want to prove instability, somehow it's like being at a mountain pass. You just have to find one direction you can perturb so that you don't flow back. So for rigidity, you have to prove that this is all non-zero for all perturbations H, but for instability, it's enough to just do it for one. We'll come back to this point later on, actually. Okay, so coming on now to study rigidity and Koizo's obstruction, we're going to, for the rest of the talk, let M be a compact, irreducible symmetric space. And for example, Koizo proved that, okay, so if it's a symmetric space, the space of EIDs will be 0. So this gives you rigidity, except in the following cases. except in the cases which are listed here. And of course, the case we're going to be very interested in is SUN, which occurs here. Okay, so the Lie group. Notice here, Koizo also computes the actual space of infinitesimal deformations, and in each case, it turns out to be the isometry. Well, it turns out to be the isometry group of the isometry, the algebra of the isometry group. So our mission is we're interested in SUN because that's what our theorem is about, but we want to somehow explicitly compute this space of infinitesimal Einstein deformations, and then we want to compute Koizo's construction for each element in there and show that it's non-zero. And if we've done that, then we can show, then we have proven that the metric is rigid. So that's how the proof works. We're just following along the lines of all those who went before us. Going back to the introduction talk, we will of course want to write our manifold as a G mod H. So G is a connected component of the isometry group. It's semi-simple, and so taking, you have this natural decomposition of G where into its subalgebra H corresponding to the stabilizer and its complement. The quantity we want to, so what we want to do is we want to somehow construct EIDs. We want to get a handle on EIDs. So we want to construct EIDs and compute stuff with them. And we need a natural way to do this. And there was actually a lot of work in this direction done by the work of Gasquet and Goldschmidt, which is summarized in their well-known book. And this is what I'm going to briefly describe now. So corresponding to this decomposition, you can look at the ad-invariant symmetric p-tensors. We're going to be particularly interested in this so if they're ad H invariant, they'll extend to be left invariant tensors on the symmetric space. And we're going to be particularly interested in S when p is equal to 3. Okay, so if you take such a tensor, and now you take a killing field eta, well, if you include eta in here, you're going to get a symmetric 2 tensor called H sub eta. Okay, assuming we have a fixed sigma, a fixed symmetric 3 tensor. And it follows from, we give a direct proof in the framework of differential geometry, but it follows from the work of Gasquet Goldschmidt actually that such a tensor is an EID. So, I mean, the real upshot here is there is a canonical way for symmetric spaces of constructing EIDs. And for the case we're interested in, we're going to be focusing on SUN. Actually, for this to work, you need to have a non-zero. You need to know that the dimension of the space is not 0, and the dimension is 1 for SUN. So we can construct one sigma, include a killing field, and then we get an EID, an explicit EID. And one of the really nice things of this approach is that somehow just having control of one will be enough to compute everything, which I'll explain in a second. So as I've said, our theorem really is reducing to, let's compute Koizo's obstruction for H eta, where H eta is constructed in this fashion. All right, so let me maybe outline the major strategy of the proof. So we're going to let psi denote the projection of, so remember we take E prime prime, for Koizo's obstruction, you take the second derivative of E, you feed in H eta, and then you project it onto the space of EIDs, onto epsilon of GE. So, okay, well, this is effectively a second derivative, and I mean, second derivatives commute. So this is going to commute. This is going to be a symmetric. This is where the S2 comes from. It's symmetric, and it's symmetric, and the objects you're putting in are EIDs. But what we saw from Koizo's theorem back here is that the space of EIDs can be identified with the Lie algebra G. Okay, that's what this is telling us. So identifying the space of EIDs with G means that we can view this, the input E prime prime of HH, say, as an element of S2 of G, and then the output is of course going to be in the space of EIDs, which we again identify with G, and so we have a homomorphism. So this is going to construct a Lie algebraic object. It actually turns out to be G invariant with respect to the natural actions of the Lie group. So this is a representation theoretic object that we want to compute. This is where the representation theory really comes in. So the strategy of proof is as follows. We are going to show that phi always lies inside a one-dimensional subspace of this space. Okay. If it lies in a one-dimensional subspace, if you know a generator of that vector of that space, then psi must be a multiple of that generator. Right. So we explicitly find a generator. We show that generator is non-degenerate. That's the first step, really. So explicitly compute the generator, show it's non-degenerate, okay. And then what are we going to do? Well, now we're going to find some, so we just have to find one h eta, with a careful choice of eta, so that this quantity, is the obstruction, doesn't vanish. And the point, of course, is that because psi lies in this one-dimensional subspace, psi is a multiple of the generator. So what we have to do is we have to prove this number c is not 0. Well, because it's not 0 for this one, for this explicit choice, you can conclude that c is not 0. And so if c is not 0 and the generator is not degenerate, you can conclude that this must be non-zero for all inputs, for all EIDs. And so therefore you can prove that. Therefore you can prove that Koizo's obstruction never vanishes. And that's it, you're done. You've shown that the metric is rigid. So this is the strategy of proof, but what it effectively comes down to is a problem from representation theory. We have to find, we have to compute the dimension of this space for SUN and find a one-dimensional subspace such that psi lies inside it, etc. So why does our theorem only work for SUN where n is an odd number, is an odd integer? Well, that comes down to actually the first step, showing that this map, the generator, is non-degenerate, that there's no non-trivial zeros. That turns out to only work when n is, it's only non-degenerate when n is odd. So without getting into, this is sort of explicit computations in Lie algebra level, so you can read it in the paper if you're really interested in. But for example, the zero set when n is even is given by these block matrices, 2x2 block matrices, and there's n over 2 copies of them. So you can see that sort of won't work if you have an odd, if n is odd. You won't be able to fit such an element you won't be able to fit these blocks of 2x2 matrices along the diagonal into such matrices. And so that's why the theorem works when n is odd, because it's crucial that this generator is not degenerate. Okay, so what's the sort of strategy of the proof? Well, I mean, we have to write down explicitly an element of this space. So here, of course, when we write SUN as a symmetric space, it's SUN cross SUN mod the diagonal. So this is H, this is the stabilizer. So this is the diagonal SUN, and this is the complement, what we called P earlier. You have to find a nice symmetric 3 tensor in this space. Okay, so symmetric 3 tensor acting on the Lie algebra that's invariant under the action of SUN. Well, here's explicitly what it is, right? Remember, we have an earlier know for abstract reasons dimension the space as 1 from the work of Gasquet-Goldschmidt. So here is sigma, trace of xy z plus trace of x zy or whatever, where x, y, z lie in SUN. So the point of me showing you this is just so you can see everything is kind of explicit, right? But the real, why did we restrict to just symmetric spaces? There's to just SUN. There's other spaces where there are EIDs coming from where the isometry group is SUN, and we don't say anything about rigidity there. Well, I mean, the simple answer is as follows. The tensor sigma that you could, so by abuse of notation, the left invariant tensor you construct on the symmetric space, I also call sigma, that's left invariant, always, okay? But remember, to construct a symmetric 2 tensor, you had to include a killing field. In general, killing fields aren't left invariant on a symmetric space. I mean, just think of a sphere, and you have the hairy ball here. Right. But for Lie groups, that's true. And so therefore, when you include if you've a killing vector field, that's left invariant. So it's sort of not hard to see if you include a left invariant vector field into a left invariant tensor, you get an invariant quantity out. And that's really the key. That's why this works for SUN. because if everything is invariant, if this quantity is invariant, if you remember a while ago, there was, we had everything was with L2 inner products, so we have to integrate everything over the manifold. But if everything is invariant, that collapses to a computation at Lie algebra level. That's why this works for SUN. Moreover, if you think back to the expression, there's all, so we're working at the Lie algebra. We have to compute quantities involving covariant derivatives, etc. But we know all of these explicitly for the bi-invariant metric, and so we can explicitly compute them. That's sort of the key insight as to why it will work. There is quite a bit, you have to choose eta, for example, to be diagonal and to have certain formats so that it will make the computation tractable, and definitely took us a lot of work, but that's the key insight into how it works. And so as an upshot, we effectively do that, compute, and we carry out the strategy outlined. So we choose eta carefully, we compute I of h sub eta, we show that's non-zero for careful choice, and we know that the generator of this, the generator of V of this one-dimensional vector space is non-degenerate. So this proves that the constant C is non-zero, and this proves that psi of HH will never be zero. It's always non-zero, and that's enough. So then that's for all EIDs. Therefore, we conclude that we have established a theorem, and SU2n plus 1 is rigid. So just to finish, one of the nice things about this approach is you can give a lot of, somehow it brings together a lot of things from other contributions and other papers can be sort of viewed in this framework. So I mentioned some of them in the first talk. I just wanted to actually give the proof of Theorem D, because it's sort of so nice, right? So Theorem D is a theorem. Okay, this is already known because it's a theorem of Sau and Hay, which is that SUN is unstable under Ricci flow. Well, how can you see this in our framework? So we explicitly, we have explicitly produced an eta so that H sub eta is explicit, and when you calculate the Koizer's obstruction, you don't get zero. Okay, so whether you have SUN, whether it's odd or even, this always works. And now if you go back to, so the reason that this doesn't prove that SUN, where n is even, is unstable is because we have the generator can be degenerate. Okay, but that's not where if you think back to Theorem C, what this says is, remember that basically it said that this quantity is up to a constant is the same thing as a third variation. So therefore, for this quantity H sub eta, the third variation is non-zero, and that's enough to prove dynamical instability, linear instability, dynamical instability. So that's how it works. Okay, so that's the end of the last talk. Into the future, of course, I guess probably you were wondering, well, what about SUN where n is even? And the problem there is that, well, we have the degeneracy. So what that means somehow is that the integrability, well, I guess vanishes to order 2, and so you need to go to higher order perturbations. The other thing, of course, it would be nice to do this for all the symmetric spaces, but that's difficult because, well, because if your tensor isn't left invariant for one thing, then you can't just reduce everything to a computation at Lie algebra level. It's more involved. Okay, but thank you for your attention, and I hope you enjoyed the talks and got something from them. I look forward to seeing some of you guys in the question session, in the Q&A session, or always anyone you can email me if you ever have any questions. Okay, so thank you very much.